So let's talk about the passive-aggressive algorithm. It's an online algorithm. It's designed for learning from massive streams of data. So the analogy that you want to keep in your head is you're monitoring Twitter, the entire Twitter, the whole Twitter. So what happens is you get a tweet and you get that much time to do something about that tweet before you have to look at the next tweet and the next tweet and the next tweet. So the idea for the passive-aggressive algorithm is you get an example, a vector of words with a positive or a negative label. You're going to use that example to update your classifier, and then you're going to throw it away, move along to the next example. So the way the algorithm works is, you remember, we're learning this weight vector that corresponds to the decision boundary in space. So you're going to initialize that vector to zeros, and then you're going to listen to the stream. When documents come along, so a document is a vector, it's a v-dimensional vector, d1 through dv. We're going to do some normal pre-processing, so tokenize it, maybe convert it to character anagrams, maybe stem it if you have the time, apply TF-IDF weighting, normalize to unit length, all the normal stuff. And by the way, this version of the algorithm assumes that everything is unit length. So the equations that I'm going to show only work if everything is unit length. Now, the first thing that we're going to do with this weight vector is we're going to classify it using the current. We're going to classify the document using the current weight vector that we have. So that just means we take the document, do a dot product with the weight vector, and see if it's positive or negative. Right? If it's positive, we're going to say, okay, we'll predict a positive for this. If it's negative, we say we predict a negative. Okay. If this is a training example, what we're going to receive next is we're going to receive the label y. And that label is going to be either +1 or -1. So it's +1 if the document should be positive, it's -1 if the document should be negative. So what we want is we want to make sure that our weight vector, if the document was really positive, we want to make sure that the dot product between the document and the weight vector was bigger than +1. And if it was really negative, we want to make sure that the dot product was smaller than -1. So you can sort of think of it graphically. So if the x-axis here represents the dot product, right? So at 0, you have your classification boundary. That's really the border. Anything that falls on the right side will be classified as positive. Anything that falls on the left side will be classified as negative. And the red zone between the +1 and the -1, that's our buffer zone. We would like to make sure that no examples, no documents for which we have labels fall into that buffer zone. So we want all the positives on this side of +1 and all the negatives on the other side of -1. So you want them to lay sort of like that. Now, we can take these two constraints, that the positive documents are above +1 and the negative are below -1, and if we multiply both sides of each equation by y, we can get a slightly, oh, come on. We can get a single equation that captures both of those constraints. Right? So if y was -1, it's just minus less than or equal. The less than or equal is going to flip to be greater than or equal because you're multiplying by -1, and then you have -1 times -1, 1. So it's going to be y times the dot product t times w greater than or equal to 1, regardless of whether it was positive or negative. So once you do that, the interpretation of this line is, so any positives that fell to the left of the red boundary, they're misclassified. That's the wrong classification. And if they fall between the red boundary and +1, they would have been classified correctly, but you counted as too close. You really don't want them in the buffer zone. So that's still a mistake. Any positives that land on the to the right of +1, however, they're fine. They would be classified correctly. So what the passive-aggressive algorithm does is it computes a loss function or an error function based on where the document falls on that axis. So if the document is positive and it falls on the positive side of +1, the loss is going to be 0 because we didn't make any error. We classified it correctly and it's not within the boundary. Any positive that falls on the other side is going to incur an error, and we're going to make that error bigger and bigger as the document is further and further away from where it should be. So mathematically, it's defined as, it's a max of 0 and 1 minus y times d transpose w. So what basically, the way to think about this is d transpose w, right? So suppose it was a positive document, right? So y is +1, and maybe I got a dot product of 0. Okay, so then my error is 1 minus 0, right? I would want my document to get a +1 as opposed to a 0. If it was classified lower, if it was classified as -1, then you would get 1 minus -1, 2. So it's even further away from where it should be. Now, critically, what you do is at this point, at the point of 1, you truncate it at 0. So any documents that landed on the correct side of the buffer zone, they incur no penalty, no error. You don't want to, because they were classified correctly and they're on the right side. So in that case, what we do is we don't want to change the weight vector at all, because that weight vector already classifies the documents correctly. But if it was on the wrong side, then we want to change the weight vector. And the way we do the change is according to this form. Right? We're going to take our old weight vector, and we're going to add a small amount of the document that we received, multiplied by its label, whether it's positive or negative, and then multiplied by the loss. So think about it this way. We're taking the weight vector and we're moving it either towards the document, if it was positive, or away from the document. And the amount that we move it by is related to L, which is how far away it was from where it should have been. So let's look at a quick visual example of what this looks like. So suppose I have a vocabulary with 2 words, dogs and cats, and I have 2 positive examples, 1 negative example. Everything lies on a unit sphere because my documents are unit length. So let's say that I had this weight vector W to begin with. Right? So the weight vector is pointing that way. This means that the hyperplane, the decision boundary, is perpendicular to it, and there's a certain buffer zone around that. Now a new document comes along, document D, and it happens to be a negative. So this document is misclassified by my decision boundary, and it's misclassified pretty badly. Okay? So what is the algorithm going to do? The algorithm is going to take a vector for D, right, and update the weight vector. So it's going to take my old weight vector W, it's going to take the vector D, it's going to multiply it by whatever the loss was, L. So here I'm assuming it's a small number. It's actually a big number, but it won't fit in the picture then. So assume it's a small number, right? And then Y is -1, because the document was a negative example. So what I'm doing is I'm adding a negative of D scaled by L to my current weight vector W. So it's going to take the weight vector and rotate it that way. Right? So that's going to be my new weight vector. And that new weight vector, if you draw a decision boundary that corresponds to it, that's going to be the decision boundary, and that classifies the documents correctly. So now it classifies the negative that came in correctly. Now, the name of the algorithm is fairly strange, passive-aggressive, and both words have an interpretation. So it's aggressive in the sense that at every iteration, at every example, it changes the weight vector such that the last example that you've seen is classified correctly and is outside the margin. And you can show that fairly easily. Right? So think about the document D came along. Maybe it was misclassified, or maybe it was inside the margin. So the dot product d transpose w, it wasn't where we should be, right? So assume that d was positive for a moment, right? So if d was positive, we wanted this dot product to be +1, and it was smaller than +1. So it was either between 0 and 1, or maybe it was negative altogether. So overall, it was short of where it should have been, and it was short by L. Right? L is the distance between where it should have been and where it ended up being. So what are we doing? We're updating the new weight vector by taking the old weight vector and adding YLD to it. Right? And then let's look at what the dot product of the document with the new weight vector is going to be. So that's just the dot product with that sum. And we can break it up as the dot product with the old vector times y times L times d transpose d. Now what is d transpose d? 1, because all the documents are unit length. So that thing is 1, right? So you just get d transpose w plus y L, right? So now think about it. The interpretation was d transpose w was L short of w. And what you're doing is you're taking d transpose w and you're adding or subtracting the L, how short it was of where it should have been. So the result of that is going to be just y. So what that means is after the weight update, if the document was supposed to be positive, the new weight vector will give it a dot product of at least +1. And if the document was negative, the dot product is going to be -1 or smaller. So the property of this algorithm is that for the last example that it has seen, it's always going to be correct, and it's always going to be perfect. So that's the aggressive part. It moves aggressively to classify the document. Now the passive part of it is what happens on this part of the hinge loss. So if the document was already classified correctly, you don't do anything. Right? You don't update the weight vector, you just ignore the example, because you're already doing fine on it. So it's always going to be correct for the last seen example. Now, if you take the documents one by one and you throw them away as soon as you've seen them, so there is no global guarantee of any kind that this procedure will converge to something. But if you let yourself see examples over and over again, you can actually show that this algorithm is going to converge to a solution that's going to separate the positives and negatives with the margin, assuming that they're separable. And the proof of that is, not very difficult. We're going to do that. Last thing that I want to do is, sometimes in practice, what you do is you don't just let hinge loss grow, you cap it at a certain value of C, and that C is related to C in support vector machines.